When looking at categorical data and how to graph it, here's an example of data, and this data is taken from the Titanic. And really, I'm going to actually look at a portion of this. We're going to look at just this portion of the table. All right, so when we do that, we say, okay, it's categorical because it's talking about how many children were in the first class. All right, so there are a total of 6. All right, and then it's broken down with this other 2 categories. So this is what's called bivariate data. By 2 variate variables. So the first variable is, gender and what class they were in, and then the second variable is saved or lost. So for those of you who aren't familiar with the Titanic, big ship, it sank. Some people died, some people didn't. There's a whole movie about it. Go watch it. Anyways, when looking at this, we say, okay, in looking at children in the first class, there are a total of 6. This row right here is what's called marginal. Marginal data. Marginal. Because it's on the margins. Just like when you add a piece of paper, you got the margins, the parts on the edge, so the marginal. All right, and then you got the part that's in the middle. And the data in the middle can be split up into what are called conditional portions. For example, we could say, of those who were women in the second class, what proportion of them were saved? So we say, okay, well, out of this 93, 80 were saved. So 80 over 93 is 86.02%. All right, so this value is a conditional, because the condition is, of all the women in the second class, all 93 of them, how many were saved? 86%. So that's what's called a conditional. I could do a marginal distribution, say, well, how many were women in the second class? And that'd be 93 out of my grand total of all people accounted for on the Titanic. All right, so that would be a marginal distribution value versus a conditional distribution value here. And then we could take this data and we could start to do a graph. All right, and you could graph them one of 2 ways, and there is a right way. When we're looking at this, we could sit there and say, okay, well, we could graph this 6, 124, or 24, 144. We could do all of that on a bar graph, and then that would show me the distribution of people that were on the boat. But what it would more clearly tell me is just how many people were on the boat. So for example, you look and say, oh wow, how many people were saved? I could do this graph of how many people are saved. 1475, and you can see that, oh wow, the most number of people saved were men that were on the crew. 192, you think, wow, if I were on a sinking boat, that's pretty selfish if 192 of the men were the ones, whereas only 6 of the first class children were saved. Like, that's terrible, right? But the reality is, you look and say, well, wait, 6 out of 6. All right, so to do strictly by the numbers, strictly by the values, would be one way that you could do this, and it would clearly show a less accurate distribution. The other method would be to find the percent, and percent would be giving what's called the relative distribution. Relative distribution. And just like if you're in a real class, not to say that my class isn't a real class, teacher writes something down, they say something, and they mention it 2 or 3 times, you make sure you write it down. All right, so relative distribution is you take the percent out of how many relative to that category. So back up here, relative to the women in second class, 86% survived. So really a better bar graph would be to graph these values. And then you look and see about that trend for who are most likely or least likely to have been saved. Because then you look and say, wow, I wouldn't have expected the men in the third class to be a higher percentage than men in the second class. My supposition, my original thoughts would be that higher class would indicate a higher percentage. It is true for women, first class, second class, third class in order, but the women crew were almost the same as women second class. All right? But then you look at the ones that are the fewest. Men crew higher than men third class and men second class. So it's hard to say why that was going on. I wasn't there on the Titanic. Not many people who are alive still are alive were. To ask and figure out why that is the way it is. But this is where we start to look at trends. We start to look at associations. So one association would be as class decreases, first class, second class, third class. So third class would be a lower class. So as a class decreases, the percent survival also decreases. Generally speaking, is true. Children have the highest percentage. Women have the next highest percentage. Actually, children and then are down here third. And then men have the worst percentages. So that's another trend that we're looking for. All right. Then we start looking and saying, and here's it's a nuance idea here that will show up from time to time on an AP exam more as a do you know your vocabulary kind of term. But basically, they would ask a question, part A is, here's the data, let's graph it, which is the best graph, and you pick the best graph and you explain why. And then part B is now, describe this graph. And when we describe the graph, we're going to use common phrases, shape, center, spread, outliers. And we'll do that here in a second, shape, center, spread, and outliers. But then usually part D or E or whatever the last part is of a problem, they will say, hey, let's suppose this third variable is introduced. And it shows that whatever distribution I made originally is now different or more likely reversed, knowing that we now have this third variable. Does knowing gender change the survival rate when looking at first, second, and third class and crew? Or is it not? All right, so if introducing that third variable gender changes it, this is what's called, has a special name, Simpson's paradox. Simpson's paradox, which basically is if an association between two variables holds for individual value, and a third variable can be changed or even reversed or even reversed when the data set for all values of that third variable are combined. So that introduction of a third variable changes or usually reverses the association. So instead of like there being a positive association, now there's a negative association. So instead of as the class gets lower, the survival rate decreases. If we introduce a third variable, and now now as the increase, as the class decreases, the survival rate increases. That would be what's referred to as Simpson's paradox. It does not hold true for this data set that we looked at, but it can for some, and there's some unique characteristics and circumstances that you'll see when you're working on problems in class. Now, before we get into comparing quantitative values in the next chapter, the next video, I should say, same chapter, different section. When we start doing comparisons, we can do comparisons a lot of different ways. This is a quick little intro. So if I have a bar graph, and I'm going to do it this way. So if I have bar graph, and so maybe the survival rates for the women was like this, and for the men it was like this. All right, so this would be for men, and this would be for women. This would be what's considered a back-to-back bar graph, or a side-by-side bar graph, depends on how you want to look at it. And then they would have whatever this category is, and you would see that, men obviously have a higher survival rate than women, and here it's reversed, and then here, and so you can see the men have a negative trend and the women have a positive trend, and you can look at things that way. And pretty much any graph you can do, can't do it with a pie graph, but you can do back-to-back dot plots, back-to-back bar graphs, we'll do back-to-back stem and leaf, we'll do a back-to-back histogram, we'll do all sorts of back-to-back graphs because you're looking at how do they compare one variable to the next. All right, so, and you'll hear me say this many times in the future, when they say compare, you need to have very direct comparison words. Comparisons words are more, less, greater, higher, increases while the other decreases, using very obvious comparison words. If you say, well, the men's is right skewed and the women's is left skewed, that doesn't, while it might be the right words that you're going to use later on, that doesn't give a comparison. Those are two descriptions, but not comparisons. And you might say, well, the average of one is 5 and the average of the other is 6, which is true, but you need to say, the average of men is 5, which is less than the average of women. And you might say to yourself, oh, self? Really? I have to be that obvious? And the answer is yes. When you're asked to compare, they want you to use a word that logically compares them, such as more, less, greater, less, stronger correlation, weaker correlation, and you describe why and how. That's in much later chapters. But as you're doing it, using very precise language of comparison. All right? So lastly, for your insert information for a question I want you to answer for the video, I talked about a positive association briefly. Basically, a positive association says that as one value increases, variable increases, the other variable also increases. And you could think, as the number of years of education that you get increases, your potential for earning also increases. So the more schooling you have, whether it be high school, college, complete college, graduate, postgraduate, as those values increase, theoretically, your potential for earning income also increases. That would be a positive association. Negative would be as one variable goes up, the other one goes down. What I'd like you to do is see if you can think of a variable or two variables. You can do it either way. But in this case, one variable, like as this variable goes up, the other one tends to go down. So if you can think of one, that's what I want you to really challenge yourself in doing, and then write that down in the answer for what question did I ask you to answer in your reflection response. Very good. We'll see you later.